Okay. We're going to talk about constrained optimization now. And this is a very new, this is very unanalogous to what happens in single variable calculus. Roughly speaking, in single variable calculus, the idea is you've got the interior, and then the boundary is just 2 points. And how do we deal with those 2 points? I just check them. Right? Always check the endpoints. That's the rule. Well, that's unsophisticated. Right? So we're going to deal with it differently in the multivariable context here, and we kind of have to, because in this multivariable context, notice that if we have a set like this, and there's an interior, and we have criteria for finding critical points in the interior. We talked about that last, before the break. So maybe you find some critical points there. These boundary points, you can't just, check all of them. Because there's not just 2 of them anymore. Now there's infinitely many boundary points. Right? So we have a new kind of a problem that we did not experience at all in single variable calculus. Okay, so how are we going to deal with this infinite number of boundary points that we have? That's the problem we face. Okay, so reminder, we're going to talk about constrained points, and specifically we saw that boundary points last time have this problem. They were constrained. Not every vector is a tangent vector. In fact, most vectors are not tangent vectors when you're on the boundary. Okay, so that being said, a local maximum that is a constrained point is a constrained local maximum. Okay. All right. So again, we're going to be talking about a process of elimination. And again, this is going to be kind of an important point of view. We're not going to find maxes directly. We're going to try to eliminate as many possibilities as we can, and whatever remains, whatever we can't eliminate, we're going to have to deal with. It's however we can. But it is importantly just that which is left over from our process of elimination. It is not that our algebraic process finds, hey, this is a maximum. It just doesn't. Okay. All right. So a little bit of semantics. We're going to talk about an objective function. This is the function that you want to maximize. Often we'll call that f, but don't assume that it will be. I mean, who knows? It could be anything. So objective means this is the function we're trying to maximize. Okay. On the other hand, our constraint. Now, our constraint could come in different ways. It could be that I've got a set and I'm looking at the boundary. And that boundary is a curve. Or it could be that it's not necessarily a boundary of anything. I just want to constrain our attention to points that are on that curve. Not because it's the boundary of anything else. Just I would like to, given the constraint that I have to be on that curve, how do I maximize a certain function? Okay. So notice that in both of those cases, we're talking about a geometric object like a curve, or now if it's one dimension higher, maybe it would be a surface. Right. Okay. And surfaces can be described by equations. So if I have a surface like this, for example, I could describe that with a certain equation. Maybe I have the equation g equals 0, for example. And it could be, a bunch of stuff equals a bunch of other stuff. Well, it's going to be convenient to use level set knowledge. And so let's take whatever's on the right side of the equation, throw it over to the left side, and think something equals 0. So with this having been the setup, we're going to call this the constraint equation. And we're going to call this the constraint function. And very importantly, the constraint equation represents a level set of the constraint function. So it's got to be level set. So g has to equal to a constant. I like 0, but it doesn't matter. Okay. Oh, whoops. Okay. All right, yeah, so constraint function. All right. Okay, now, reminder. Y'all remember this. We talked. It was a long time ago. In summertime, that means it was a couple of weeks ago. But gradients are always perpendicular level sets. So I hope you all remember that fact. So, for example, let's suppose our constraint set is this set there, described by this equation, which you'll notice is a level set of this function. Well, that constraint set, being as it is a level set of that function, the gradient of that function will be perpendicular to that level set. Now, just a little bit of lingo. The way we will describe this, the gradient of the constraint function, very often I'll call that the constraint gradient. It's just easier to say than gradient of the constraint function. Okay. All right. A three-dimensional version of this. If your constraint set, written as a level set of a function, this being, again, as usual, your constraint function, then the gradient of that constraint function is always perpendicular to that constraint set. So the constraint gradient is perpendicular to the constraint set. Everybody on board? Just lingo. An old fact from earlier in chapter 4. Okay. All right, but we're interested in the function f. F is our objective function. That's what we're trying to maximize or minimize, but let's say maximize. Okay, so I want to consider the following scenario, and we'll think about the algebraic consequences, and we'll come up with a way of how to deal with this precisely. But suppose you are looking on the following constraint set there. So we've got colors. This is where g is equal to 0, right? And we're interested in this point on the constraint set. How might I eliminate that point from consideration? What would have to happen? Under what circumstances could I say, yeah, and therefore this is definitely not the maximum point that I'm looking for? And so here's a story that would allow us to come to that conclusion. Let's suppose that I have a non-zero gradient, like this. And it's tempting now to end our conditions there and say, yeah, look, we dealt with this back in the constrained case, an unconstrained case. That look, if you've got a non-zero gradient vector, then just take off and start moving in that direction, and then that directional derivative is positive, and clearly that couldn't possibly be a maximum. But this argument fails. Doesn't work. Because I can't move in that direction, right? We have this big problem now. We are constrained. From this point, I am not allowed to just move whatever direction I want. Not every vector is a tangent vector anymore. And as I have it drawn here, notice, the way I intended to communicate anyway, this gradient vector has you moving off of the surface. There is no curve in this surface that has that as its velocity vector. So this is not an option. So we have to come up with a new argument. So the idea is this. We can't go that direction. Okay, well, what's the closest to it that we can get? And so the idea is look at the tangent plane to the surface at that point. Look at the perpendicular. Drop a perpendicular down into that tangent plane. Look at this resulting vector, this projection kind of the gradient vector down into that tangent plane. And let's take that as our velocity vector. Let's, do that. And that is the velocity of a curve in this surface, right? You can imagine something like that. Because it's in the tangent plane. Is everybody on board? So, what do we conclude from this? What happens, let's zoom out. Let's compute the directional derivative. We know that because we're assuming the function is differentiable, that's how I compute directional derivatives. And that formula for directional derivatives with a dot product, I have magnitude times the cosine of an angle. Well, this vector here, v, its magnitude is something that we can write down without too much trouble, which I guess I didn't write that down. But that magnitude of v, do this over here, magnitude of v is the magnitude of the gradient times cosine theta. And so take this, plug that in, and look what we get. We get this expression here, which is a bunch of squares. Right. All right, so most of the time, not always, most of the time though, this expression is going to be positive. So therefore we have a tangent vector indicating a direction that I can go on the surface. And as I go in that direction, the function is increasing. Clearly this is not a maximum point. And I rule it out and we move on to other points. Most of the time. Right? So, now let's just think about though, what are the asterisks, right? Or what are the conditions on this to work? Well, for that to work, I need for the function to be differentiable for one thing. If the function's not differentiable, then I can't even have that formula in the first place. Function's not differentiable, I don't even know how to compute directional derivatives. So I don't know what's going on. Can't eliminate it. Okay. I also need for this to be positive. So how would that, what do I need for that to be positive? Well, I would need the gradient vector to not be 0. If the gradient vector is 0, then that I don't get positive. Right? And likewise, I need for this cosine to not be 0. In other words, I need for the gradient not to be perpendicular to the surface. Right? This angle here, if the cosine of that angle is 0, in other words, if that angle is a right angle, then the projection, this magnitude of v, is 0. Okay. So these are the conditions. This is my ruling out process. If these three things all happen simultaneously, which is, again, the vast majority of the cases, most of the time our functions are differentiable. The gradient vector, what are the odds that the gradient vector is exactly 0? It happens rarely, but not most of the time. And what are the odds the gradient vector is exactly perpendicular to the surface? Most of the time that doesn't happen either. So if these routine conditions hold, then we have ruled out our possible maxes. Everybody good? Okay. All right, and so we have a definition of a critical point. Now keep in mind, what is a critical point? A critical point is a point where our argument fails. If this elimination process is going to fail, then either the function isn't differentiable, or the gradient isn't non-zero, in other words, is 0, or maybe the gradient is perpendicular to the surface. So if any of those things happens, the function is not differentiable. If the gradient is 0, if the gradient is perpendicular to the surface, if any of these three things happens, then I can't use my process of elimination. I have no idea what's going on. Best I can do is just call that thing a critical point and worry about it later. Right? Oh, I'm sorry. Forgot to turn my thing off. Okay. Okay, pause for questions. How are we doing? Is everybody okay? Okay. All right. So we could run with this. We could use this. We could, this is how we find critical points. But it's a little awkward to work with, and specifically this is awkward to work with. we don't have an immediate algebraic method for how to decide if a vector is perpendicular to a surface. How do we do that? So I'm going to rewrite these conditions a little bit. It's just for rewriting purposes, to make it easier to work with. I am actually going to enlarge our definition of critical points a little bit. So the three conditions that I'm going to replace these with are not quite exactly the same. But what's important is that every one of the critical points defined here will be one of the points that I'm about to define now. So here they are. We're going to look at points where the function fails to be differentiable. We're going to look at where the constraint gradient is 0. That looks like a mistake, but it's not. And we're going to look at where the gradient of f, the objective gradient, is a multiple of the gradient of g, the constraint gradient. Okay, now in order for me to get you to accept these three conditions, I need to persuade you that whenever any one of these things happens, at least one of these things must happen. And let's go through that. It's a pretty quick process. If the function f is not differentiable, well, then the function f is not differentiable. We didn't change that one. That was an easy one. Okay, next. If the gradient of f is 0, which one of these holds? Notice it's got nothing to do with number 2. If the gradient of f is 0, what happens is this is true. The gradient of f is 0, then the gradient of f is a scalar multiple of the gradient of g. That scalar multiple is 0. Okay, so algebraically, this catches all of those cases where the gradient of f is 0. Okay. Lastly, what if the gradient of f is perpendicular to our constraint set? Which of these happens if the gradient of f is perpendicular to the constraint set? Well, I'm going to refer you to this picture here, and here's the gradient of f perpendicular to the constraint set. Don't forget, here's our constraint set. Don't forget, as previously agreed, the constraint gradient is always perpendicular to that constraint set. So here's the thing then. If the gradient of f is perpendicular to the constraint set also, that means that the gradient of f is a multiple of the gradient of g. Let me put an asterisk on that real quick. But most of the time, this is what happens. Perpendicular to the constraint set means parallel, a multiple of gradient of g. So most of the time, you get this. Now let me go back and talk about that asterisk. What is the asterisk? Well, annoyingly, I have to confess, if the gradient of f is perpendicular to the constraint set like this, it is also possible, let's see, did I draw a picture of this? I guess I didn't. It is also possible that the gradient of g might be just the 0 vector. Right? How do I know? Hey, that could happen. The gradient of g could be the 0 vector. And if this happens, then tragically, the gradient of f is no longer a multiple of the gradient of g. If the gradient of g is 0, there's nothing you can multiply it by to get gradient of f. So in this scenario that I need to deal with, right? I mean, this is a critical point. My condition, gradient of f is multiple of the gradient of g, fails. And that's bad. Right? This would fail. But then that catches it. Right? So we're going to consider gradient of g equals 0 as a condition just to make sure that I don't miss out on these kinds of gradients of f. How are we doing? Everybody on board? Okay. Now, this seems uncomfortable to a lot of students because here's another thing that another point that we will have to deal with is a point where the gradient of g is 0, and the gradient of f is off over there like that. Our new enlarged definition of critical point will include this scenario where the gradient of g is 0 and the gradient of f is pointing off in some wacky direction. Now I know that this is not an absolute maximum point. I know that. I clearly look, this is a non-zero vector, it's not perpendicular, just go that way and the function's clearly increasing. So by rewriting our conditions in the way that we have, where whenever the gradient of g is 0, we're always going to include those. I am including more work for us. We're going to be checking points that arguably we shouldn't have to check. This is still a win, though, because these conditions are much easier to deal with algebraically. That's algebra. Write it down and solve it. This is algebra. Write it down and solve it. So it's a couple of more points maybe, but it's points that I can deal with. Whereas this up here, again, we don't know how to deal with that. So enlarging our set just a little bit is a small price to pay for having algebraic foot in the door. Okay, so here we go. This is what we call the Lagrange multiplier theorem. So if you have a constrained critical point, one of these three things is going to happen. So if I find the collection of all points where any one of these things happens, then I definitely have all of my critical points. Okay, so when we go through, and when we use this theorem to try to find critical points, it's kind of a three-step process. Step 1, I've got to find points where the function fails to be differentiable. This is why I call the differentiability condition. Second thing I've got to do, I've got to find points where the gradient of g is equal to 0. This is what we call the degeneracy condition. And why we call this the degeneracy condition is hard to explain in this context. There's a really good reason for it. It means that there is good reason to believe there's something kind of wrong with what the surface looks like at that point. But that's a whole different discussion that's not Math 212 appropriate. So nevertheless, the name just means you need to know the name. It's called the degeneracy condition. And then lastly, we need to look for points where this happens, and this is called the Lagrange condition. Now, real quick comment before we get our hands dirty and start computing stuff. It is very important that you check all three of these conditions. After all, this is a process of elimination. Right? These are the points that I can't eliminate. If you don't look at all of the points that you can't eliminate, then you're ignoring possible maxes. You can't conclude, and therefore this is the maximum, if you didn't even look at these over here. Right? So this is an important part of the process. You got to check all three conditions. Now, that said, most of the time, condition 3, the Lagrange condition, most of the time, and you'll note, I'm telling you this because, you're going to notice it yourself anyway. Most of the time, this is where you're going to find your maxes. But if you ignore these, then you have no believability with what you found here. So I hope that makes sense. So make sure to check all the conditions. And now let's do an example. So here we go. I want pencil. I want to find all the critical points of this function. So maybe I'm trying to maximize this function. Maybe I'm trying to minimize this function, whatever. And my domain is this. It's defined by that equation right there. So now, y'all recognize what we're doing here. This is a plane. On this plane, I would like to find critical points of this function. Well, that function is just the distance to the origin squared. So Well, this plane extends infinitely. It's a great big plane. Right? There is no maximum of distance to the origin squared. If you're allowed to be on this plane, just take off and start moving in the plane. You can go as far as you want, and this function will just keep getting bigger and bigger and bigger and bigger and bigger. But there is a minimum. Right? On this plane, does not go through the origin. Here's the origin. Here's the plane. Right? There's going to be some point that is closest to the origin. There will be a minimum value of this function. That's what we're going to be looking for here. How do I find the minimum point for f, subject to that constraint? Okay, step one. Notice that this is not written as g equals 0. So let's do it. Take this, whip it over to the other side, and this is the thing that has to equal to 0. So that's our constraint function. By the way, you could arguably use this as your constraint function. Point being, 49 is still a constant. There's something kind of appealing, though, I think, about the constant being 0. Anyway, no big deal. Okay, so let's go. Now we have a objective function. We have our constraint function. And let's start the process. Step one. Is this function always differentiable? Are there any points where this function fails differentiability? Nope. It's polynomial. Polynomial is differentiable everywhere. So, I don't know if you want to call it bad news or good news, but there are no differentiability problem critical points. Okay, next, the degeneracy condition. We have to look at where is the gradient of g equal to 0. Okay, well, there's your g. There's the gradient of g. Where is that equal to 0? For what values of x, y, and z is this equal to 0? Well, none. Again, the 6 is never equal to 0. I don't care what x is. Right? So there are no degenerate critical points. Okay. How are we doing? Everybody happy? Lastly, we look at the Lagrange condition. The Lagrange condition says the gradient of f is a multiple of the gradient of g. By the way, notice we use this lowercase Greek letter lambda as that multiplier, they call it. Thus the name Lagrange multiplier theorem. Okay, well, the gradient of f is that. The gradient of g we already computed. And so here's our Lagrange condition. And by the way, the Lagrange condition, you'll notice, if this is true on vectors, that means that all three of the coordinates have to pair up like that. So what we have, the Lagrange condition actually gives us then 3 equations. And we're a little worried because we have, 3 equations, but there's 4 unknowns in this little system, right? There's x, y, z, and lambda. I don't know what any of those are. I need to solve, but I've got more unknowns than variables. So the realization that we need to make is, why am I looking at these conditions? Why am I looking at the Lagrange condition? Well, because I am trying to find points on this plane that blah, 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 right? Point being, the points that I'm interested in have to be on this plane. That's right there in the statement of the question. If a point's not on this plane, it's got nothing to do with my question. I'm trying to optimize this function f on that plane. So the hidden 4th equation here is I'm not just trying to solve these for any old random x, y, and z. I want to know where are those Lagrange conditions satisfied on my constraint set. So I am solving actually a system of 4 equations with 4 unknowns. And it's a little intimidating, by the way, algebraically, right? It's a lot of equations, a lot of unknowns. We got lucky here, they're linear. They're not always. The algebra of solving for 4 unknowns and 4 equations can be brutal. FYI, this makes writing these kinds of questions really hard because when I'm trying to write such a question, it's very easy to write a question that's way too hard algebraically. And it's not that bad to write a question which is just like every other question y'all have ever seen of this. Y'all are going to see a certain number of these on the homeworks. Anyway, it's hard for me to write a question that is just hard enough. Right? Anyway, that's not your problem. Okay, so I'm going to show you how to solve a system like this. By the way, this is not the only way to do it. It is not always going to work the way that I'm about to show you, right? But what I'm about to show you does work pretty often. So this is a good thing to try, and that is we're going to do what's called eliminating lambda. I'm going to eliminate lambda by solving for it. And if I solve for lambda in each one of these three equations, well, they're all lambda. So the three things that I get in solving for lambda have to all equal to each other. That's the key idea. So solve for lambda in each of those three equations. Lambda is equal to x over 3 in the first equation. It's equal to 2y over 3 in the second equation. It's equal to z in the third equation. So most importantly then, I know that these three things I got in solving for lambda all have to equal to each other. Right? And then specifically then I can solve for y and z in terms of x. So that's the big idea. Now, once you know y and z in terms of x, you can plug that into your constraint equation. And that gives you this. So notice, all I've done is I've taken that formula for y, put it in there, that formula for z, and put it in there. So this is just what my original constraint equation was. This is 6x plus 3y plus 2z equals 49. And now I can solve for x. Once you know x, you can solve for y and z. Everybody see how that kind of worked? I mean, not always be like this, but this kind of thing does work pretty often. All right, I think I have another example I want to show you in here. Yeah, right, this is a really good example. So here we go again. We want to find critical points, same objective function, different constraint function, you'll notice. Now our constraint set is an ellipsoid. It's interesting, right? So we're looking for points on this ellipsoid that are critical in terms of distance squared from the origin. All right, so the usual game, differentiability, no problem. This is differentiable everywhere. Let's see here, degeneracy. I need to know where this is 0. Now, here's a little bit of a landmine, something to be careful of. It's tempting to look at this and say, hey, oh yeah, look, this can be 0. Totally, we've got a degenerate critical point because if x, y, and z are all 0, then the gradient of g is 0. That's a degenerate critical point, isn't it? But it's not, because for this to equal to 0, our x vector has to equal to 0, and that point doesn't satisfy our constraint. Right? So again, don't lose sight of what we're doing here. We are in fact trying to understand points on this constraint set, and only points that are on this constraint set. Right? My interest is entirely restricted to this constraint set, and I don't care what little games you play that say, oh yeah, here's a point off of the constraint set that matters. No, it doesn't. It's not on my constraint set. I don't care. Everybody on board with that point, right? So it's an important mistake if you set the gradient equal to 0 and get something, but don't check whether it's on the constraint set. You didn't quite finish that process. Okay. All righty. The most interesting bit about this example, though, is where we get to the Lagrange condition. Now, remember the Lagrange condition says look at the gradient of f, look at the gradient of g, look where the gradient of f is a multiple of the gradient of g. This is what you get with that algebra. Y'all know how to compute gradients, so I'll skip over that part. And let's look at the resulting three equations. Now, of course, don't forget also there is the constraint equation. This is actually four equations. Okay. It is tempting to look at this and say, no solutions, because check it out, lambda's got to equal to 1, and but wait a second, this says here that lambda is equal to a ninth, and that can't happen, so done, there's no critical points at all. And not so. So this is a classic algebra blunder. High schools encourage this because I don't know why it is, but high schools just tend to not be careful with the strict rules of algebra. I don't know. I don't know why. Let me not speculate. Anyway, you can't cancel stuff if it might be zero. Right? So let's look at this first conclusion we got here that says, lambda has to equal to 1. You get that conclusion by canceling the x's, but you can't cancel the x's. What if x was 0? X could totally be 0. This is a completely invalid conclusion. What you can conclude here from this is that lambda is equal to 1 or x is equal to 0. One of those two things is true. We just don't know which one. Everybody happy? So, all right. So let's. We got to deal with that whole x equal to 0 business. The way I'm going to do that is by let's sidestep it. Let's first consider what happens if x is not 0. If x is not 0, then I can conclude lambda is equal to 1. If lambda is equal to 1, I can plug into these two equations, and that tells me y and z both have to equal to 0. Right? Am I moving this around too fast? I hope if x is not 0, cancel the x's. Lambda is 1. If lambda is 1, 2y is 8y. Y has got to be 0. 2z is 18z. Z has got to be 0. So if x is non-zero, y and z are 0. And take these, plug them into the constraint equation. If y and z are 0, then x has got to be plus or minus 6. Everybody see what happened there? Okay. So we get two critical points. Now those two critical points came from assuming x was non-zero. That does not exhaust all the possibilities, right? It's also possible that y might be non-zero, in which case x could be 0. Right? So you got to go through these three separate cases. What if x is not 0? What if y is not 0? What if z is not 0? And y not equal to 0 gives us these critical points. Z not equal to 0 gives us, that didn't circle well, those critical points. And so, in fact, we have 6 critical points, not none. Right? So, be really careful with this bit of algebra. And don't mistakenly cancel illegally. And let me pause on this for questions. Anybody have any questions about this? Everybody happy? Okay. All right. So we're not going to be able to finish the two constraint case today, but we do have tomorrow. Tomorrow we're going to, but I do want to start on the two constraint stuff. I'm going to use our 5 minutes. I think we need them. So we will, tomorrow we'll finish up the two constraint business. There's a little bit to say with, in section 4.13. That's actually mostly just examples. So that's going to go pretty quickly. So we'll have time to finish this up, finish up the optimization, and then also go back and finish up the chapter 6 stuff. tomorrow. Okay, so very quickly though, let's talk about what is the two constraint case. What if we have in fact more than one algebraic constraint defining our domain? So for example, what if, and by the way, this was the second hardest picture in the book to draw. The hardest one was the right hand from the right hand rule, right? That was the hardest one. But this was tough. So what if you have this constraint that you need for g to equal to 0? Thus, you're stuck on that surface. But what if there is a second constraint that, look, I also require that you be on this other surface, described by h equals 0. And that constraint set, in other words, is where those two surfaces intersect. So what if I am confined onto that purple curve? Right, that's not a crazy scenario. You can imagine that you'd be, trying to optimize some function, and well, look, I need, for the realities of the circumstance are that this has got to be true, and that's also good. Here's a couple of, I'm stuck on these two things, but other than these two things, I can kind of go anywhere I want to go. I want to maximize my engine efficiency, subject to two constraints. How do we maximize engine efficiency? Or for economists, how do we minimize risk or maximize profit, whatever, given a couple of constraints? So very, very serious problem, and it's geometrically a little bit different, but it's going to end up with algebraically kind of familiar punchline, and the idea goes kind of analogously, which is I'm going to consider one point at a time. I'm going to try to eliminate that point as a possibility. I'm going to try to eliminate that point by entertaining, okay, what is the gradient of f doing? Now, we've already realized I can't just take off and start moving in the direction of the gradient of f. That pulls me off of my constraint set. Right? So, okay, instead, let's look at this projection. Whoops, I'm sorry, I wanted to change the color. Let's look at the projection of the gradient of f down to the tangent plane to my constraint set. Right. And let's say, okay, what happens if I move in that direction? And not hard to persuade yourself, as I have it drawn here, this dot product's going to be positive, and there's no way that's a maximizer because the function's increasing. Right? This argument will usually work with one exception. The one exception is, what if the gradient of f is perpendicular to the constraint set? Right? If the gradient of f is perpendicular to the constraint set, then there's no direction that I go. Whichever direction I go, the directional derivative is not going to be positive, and the function isn't increasing. I just can't eliminate. I don't really know what's going on here. Right? So we just need to figure out how might it look if the gradient of f is perpendicular to the constraint set. And most of the time, what happens is, keep in mind the gradient of the gradient of g is perpendicular. The gradient of h is perpendicular. Most of the time, those define a plane that is entirely perpendicular to the curve. And by the way, the entire plane perpendicular to the curve. So if the gradient of f is perpendicular to the curve, then it's got to be in this plane defined by the two constraint gradients. So the gradient of f's got to be a linear combination of the gradient of g and the gradient of h. So most of the time, this is what happens. Most of the time, gradient of f is, it's a multiple of the gradient of g plus a multiple of the gradient of h. And these other possibilities are just different ways in which our picture could be wrong, basically. So, looking at this picture, what would happen if the gradient of g were 0? Oh, well, then the gradient of g and the gradient of h, the gradient of g is 0. They won't define that whole plane. Right? So our argument kind of stinks if the gradient of G is 0. Likewise, if the gradient of H is 0. Or, annoyingly, what if it ends up being that the gradient of G is in the same direction as the gradient of H? Wow, then, these linear combinations, they just don't make that whole plane. And our argument, again, kind of stinks. So, other than those possibilities, though, other than these possibilities, this is what critical points have to look like. So we just get a slightly different list of conditions. This is our two-constraint Lagrange multiplier theorem. And we'll pick up here and start doing some examples first thing on tomorrow morning. Okay, all right. See y'all later.